Okay, so in this video, we're going to take a look at row operations, right? So again, here, this is all just a build up to kind of using uh, or being able to solve linear systems using matrices, right? So you've gone over how to switch between the two different modes, right? Augmented matrix and a linear system and vice versa. So what we're going to take a look at here is, first of all, we're going to introduce, what is the goal here is to get the augmented matrix in what's called row echelon form, right? So we're going to define here what we are going to call the main diagonal. Now, what I have here is a 3x3 matrix. So just think of this really as just a coefficient matrix, right? So we're kind of missing the augmented part, the constant part, but assume that, for this matrix, it belongs to a 3x3 system. The only thing we're missing here is the solution column here, what they're all equal to. But for now, I just want to define this column here to be what is called the main diagonal. Right, so in a 3x3 column, right, the 3x3 matrix, right, the main diagonal will be all the ones that are the column like A11, right, A22, A33. Okay, so that's what we're going to call our main diagonal. So our goal is going to be, via row operations, which I'll define in a second, is to change our augmented matrix into this row echelon form, where all along the main diagonal, I have a 1, right? And below that main diagonal, the values are going to be 0, right? And above the main diagonal, there'll be some other constants. Maybe some of them are 0, but we're not guaranteed. They're just going to be some other constants. Right now, the way I'm going to achieve that is through what is known as row operations. Now, there are 3 row operations. All right, so I'm going to scoot up here. All right, row operations. The first one, I can interchange rows. So the notation being used here is R sub I, and then that double-sided arrow with R sub j. Okay, and again, I'll go over some examples here in a second on how I do that. All right, to multiply a row by a constant, notation C times R sub I, so I multiply all of that row by whatever, by whatever that constant C might be. Okay, and then the third row operation is that we add the product of a row multiplied by a constant to another row. All right. So R sub I plus that constant C R sub j. Okay, so let's take a look at here, for example, how about, let's say we had a matrix here. Let's see, 1, 2, 3. Let's say we had an augmented matrix. 1, 2, 3, 4, -2, 4, -3, -1. Excuse me. All right, and then our last row, we'll call it 1, -4, 5, 3. Okay, right, just kind of this matrix I made up here, right, just to illustrate the row operations. Okay, so here, let's say, so here I want to change this matrix So this matrix I'm going to change by performing the following row operation. I'm going to interchange R3, interchange with R2. Okay, so by doing that, my new matrix, and it is equivalent, right? So these row operations lead us to what is called a row equivalent matrix, right? So I guess maybe I shouldn't use equality here. All right, so because we'll see they're very much not equal, right? Equality in the matrix is each element in one matrix is equal to the element in the other matrix. So what I do here is 1, 2, 3, negative 4. And here we'll have 1, minus 4, 5, 3. And negative 2, 4, negative 3, negative 1. Okay, so what you see here is I swapped row 2 and row 3. Okay. All right, now these two matrices that we have here are what are called row equivalent. Well, not equal, right? As we can see, very much not equal, right? They look completely different, right? What row equivalent means is that the new system here represented by the row swap is equivalent to the system that we started with. All right, and that's kind of the idea of these row operations. Each time you perform one, it changes what the matrix looks like, but it does not change what it represents. It still represents that original system. Each matrix that you that you find after a row operation is what's known as row equivalent, right? So these two, we call these two matrices, right? These are row equivalent. So the underlying system is still the same, right? Which is how we are able to solve a system of equations by performing these row operations, right? So that's one of them, right? So now let's illustrate another one, right? How about we illustrate, let's say negative 2 times R3. Okay, so now in my new matrix here that I have, I'm going to take the third row and I'm going to multiply the whole thing by negative 2. Okay, so what that looks like is we'll have everything else remains unchanged. Oh, excuse me, got ahead of myself here. The third row, every single element in that third row gets multiplied by negative 2. So we get 4, negative 8, all right, and 6, 2. Okay, all right. Okay, so that is an example of the second row operation. All right, so now the third one. All right, so now the third one, what we're going to do here is I'm going to take R2 and I'm going to add to that negative 1 times R1. Okay. All right. And what is going to happen here is all of R2 is going to be now replaced by this operation. Okay. So what I'll do here, and I'll perform the operation on the side so you could see what's happening, and then I'll replace it in my new row equivalent matrix. All right, so I'm going to multiply negative 1 by that first row, so that gives me negative 1, negative 2, negative 3, 4, and then R2 is as is, negative 4, 5, 3, right? So I'm just adding the coefficients here, right, off to the side. So I get 0, negative 6, 2, and 7. Okay, all right. So now, in terms of my new row equivalent matrix, these coefficients here are now going to go into R2, right? The row that I didn't multiply any factors by. So R1 remains unchanged. And now my R2 gets replaced by this new row. And then R3 was not part of any of these operations. Okay. All right. And that is an illustration of the 3 row operations. All right. And now you can start to see, all right, what the goal is going to be here, right? Getting it into row echelon form. I saw a 0 showed up there, right? We will now, and you'll see in the examples here, we would want to have another 0 where that 4 is right here, right? And we kind of illustrated how we would go about doing that. Okay, so now the process here that I'm doing here, all right, so this is just a short example here of what is known as Gaussian elimination. Right, so the idea behind Gaussian elimination, right, is that you use these row operations on your coefficient matrix, or really augmented matrix, I should say, right? But the goal is to make the coefficient matrix that starts off looking something like this, right? Where these are some values, right? And the idea is that you take this, you perform the row operations, and eventually you end up with a row equivalent matrix that now looks something like this. Oops. Here we go. It should be 1. Okay, so that's the idea, right? That is the process getting it to row echelon form. That is the process known as Gaussian elimination, right? And again, this is just a coefficient matrix, right? You'll add on whatever that constant is there, but that is the goal, right? The next couple videos will show you examples on how to perform row operations to get it to that form, right? So this is what is known as Gaussian elimination, right? Performing these 3 row operations, several different times, so that at the end you wind up with a matrix that is in row echelon form.